welcome back to my channel. And today we're gonna dive into one of the most popular and effective pathfinding algorithms in AI. The algorithm, as you can see, is called aesthetic algorithm, and aesthetic is used in a variety of applications from video games to web-based map systems because it finds the shortest path between nodes in an efficient way. In this video, we'll not only explain how a static works, but also demonstrate it using a 8 puzzle problem. And you can see you can also get this uh, layout from a website which I took called Gateway. Alright, let's begin. So, what is a static algorithm? A stack algorithm is essentially a best first search algorithm. It is designed to find the least costly path between a starting point and a goal by evaluating both the distance already traveled and estimated distance to the goal. It uses a function called f of n that helps prioritize which path to explore next. So as we know, the formula is f of n is equal to g of n plus h of n, where g of n is the cost to reach the node n from the start, and h of n is a heuristic that estimates the cost from n to the goal. Okay, as you can see here as well. Now, this combination allows Asterix to efficiently zero in on the shortest path without getting stuck in long, inefficient detours. Okay. Now, how does this algorithm work? So, let's talk about how the algorithm works. We start at a given node, which is added to a list called open. Okay. And this list holds nodes that have been evaluated by the algorithm but haven't been fully expanded. And we have another list called closed that holds the nodes that have been visited. At each step, we remove the node with the smallest value of f of n from open and expand it by looking at the neighboring nodes. Okay. If one of those neighboring nodes is a goal node, we are done. Otherwise, we continue evaluating nodes based on their cost. Now, we know that a static algorithm balances between exploring new paths and focusing on the most promising node, making it extremely powerful for complex problems. Alright, here are the steps as I talked about. You can look into these and you can even visit this website if you're not sure about how these steps took place. Let's move on into the solving of the 8 puzzle problem. Alright, so this is called an 8 puzzle problem. Okay, the goal of the puzzle is to move tiles until we reach a specific final configuration. These are the the initial states, and these are the final. Now we have to reach this goal, as this is the initial. We begin with this, and this is our final destination. As you can see, the goal is to transfer the initial state into the final by sliding the tiles. Sorry, we can slide the tiles into the empty tiles that we have. Okay, and it will help us find the most efficient path. So we start at the initial state and calculate both the cost of g of n and heuristic h of n, which in this case is based on the number of displaced titles. Okay, we expand the node, generating new configuration by moving the blank tiles. For each configuration, we calculate f of n decide which part to explore next, aiming to minimize the cost. As we proceed, we'll reach the goal state or continue expanding nodes until all the possibilities are explored. Alright, let's visualize this solution that the website has given us, which I'll move on to next. So we start, as I said, we start from the initial and move the tiles step by step, minimizing our cost as we go, as shown in the image here. The algorithm successfully reaches the final state after we expand all of this. So let's look into it in closely. Let's consider g of n as the depth of the node and h of n the number of misplaced tiles. All right, this is a beginning. Now, in this initial state, like I said, g of n is the depth of the node and h of n is the number of misplaced tiles. Here we'll count the misplaced tiles. Suppose the initial state was, sorry, the final state is 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is the initial. Now we know 2 is misplaced as well as 8, 1, 6. Rest of the numbers like 3, 4, 5, and 7 are not misplaced. So total number of misplacements are 4, and where we know the depth of the node is 0. So f of the formula says g of n plus f of n. Like if we look into the formula here, g of n plus f of sorry, h of n. So we put in the values into that and we come into a consideration of 4. Okay, now looking into this, let's iterate. We have to iterate each time to get the final state. Now we iterate where the after first iteration the depth of the node becomes 1, and we'll take all the possibilities. All right, where we move the tile 7 to the blank, and we move 6 to the blank, and where we move 5 to the blank, because we have three possibilities. All right, and we made three possibilities by moving 7 into the blank, 6 into the blank, and 5 into the blank. For example, we took the 7 into the blank. Now we know that if we took 7 into the blank, how many displacements do we have now? We have 3, 4, 5 at its own place, like the final state, but 2, 8, 1, 6, and 7 are not in the correct tiles. So there is a displacement of 5 tiles. Okay. Now we, according to the formula, 1 plus 5, which equals to 6. Moving on to the next possibility, how many displacements do we have? We have 1, 2, 3, and the rest of the tiles are in their originated place. Okay, 3 as are displaced, and we use the formula, we get 4. For the final as well, we do the similar thing. How many displacements? 1, 2, 3, 4, 5, and we get 6, which is the best among these. And as you can see, 4 is the most least, as these two add up to 6, and we'll just ignore these two and we'll iterate this one. And we keep repeating these methods which have the lowest f of n. As you can see, we took this and we took all the possibilities. And how many possibilities do we have? Where we can move 1 to the misplace, we can move 4, and we can move 8. Let's not take 6 because we have already used 6. So we took 3 possibilities. First we'll take for 1. Let's look at the displacements. 1 is not at the designated area. Among these all are, so we have a total of 3. Here we took g as the second iteration, which is 2. 3 plus 2 is 5. Moving on to the next one, where we brought 8 to the blank tile. Now we'll check. 2 is not in the designated area 218. And here as well we have 3, which also adds up to 5. And here we have another where we took 4, and here we can see that we have 4 misplaced tiles. Okay, which adds up to 6. Now we have 2 which are the same value, so instead of just taking one, we trade both of these. Okay, now we have 4 possibilities. Looking at the first, which gives us 2, because how many times can we move into the blank tiles, as we used 1 already. So we'll just forget 1 and we'll go with 2 at 7, for in which we took 2 at first and 7 at the second. How many misplacements do we have in this? Here comes 1, 2, 3. That's it. Rest of the values are at the original places. So 3 plus 3 adds up to 6, as we are at the third iteration. And here as well, we took 7 up. How many do we have? 1, 2, 3, 4. 4 of this. So Here comes 4. Moving on to the next one, we have moved 2 into the blank tile. As you can see, now we have 2, 3, 4, 5, 6, 7, which are at their right places, and only 2 which are misplaced. We'll add in 2 which adds up to 5, and for this as well we put on 3. Now in this we have 1, 2, 3, 4, 4 misplacements, that adds up to 7. So we know which is the best possible value for us, because we know the final state is 1, 2, 3, 4, 5, 6, 7, 8. And if you look into this, you know that if we eventually, using your common sense, if we move 1 up into the blank state, eventually you'll get the answer. So let's proceed with this, where we moved 1 up the blank state, and now only we have only 1 misplacement. So at the fourth iteration, 4 plus 5, fourth iteration with 1 displacement, so 4 plus 1 is equal to 5, where we get 2 possibilities, right? But we know that the answer we are looking is really close, as if we move 8 into the blank tile, we'll get the final answer. So let's just focus on this, ignoring this. Here we moved 8 into the blank tile. As you can see, there are no misplacements now. So h is 0. We are the fifth iteration, so 5 plus 0 is 5 plus 0 is 5, and we know this is a final state. So here is how, using a static algorithm, we solved the 8 puzzle problem. Now this is the most efficiently solved method of the puzzle by focusing on the most promising path and minimizing unnecessary moves, where we took all the possibilities and we got a final star. Now, what is the advantages of this algorithm? It is particularly useful because it combines the strength of both Dijistra's algorithm and greedy search. It finds the optimal solution and works efficiently by considering both the cost already spent and the cost still to come. This makes it a go-to solution for many real-world applications, including pathfinding in video games like I mentioned in the beginning, where characters or objects need to navigate complex terrains. Or navigation systems like Google Maps. We use Google Maps in our daily lives, and it does gives us, short routes. For example, if you're going from path A to path B, it gives us the best routes. So this is a balance between exploration and optimization, which makes a static algorithm stand out. All right. So here was how a static algorithm works, from pathfinding in video games to solving puzzles like the eight puzzle problem. And this is the most famous problem, as it is very easy to understand, and we know that a static is one of the most powerful algorithms for finding the optimal path. And that's it for today. Thanks for watching. And if you found this video helpful, don't forget to like, subscribe, and comment below with your thoughts or questions. Thank you.